All right. Hi, everybody. My name's Andrew, and I'm here to talk to you today about Orleans. You can use Orleans to build scalable game services. So you may be saying, Andrew, what is Orleans? Well, maybe you have a few hundred users, or maybe you have a few hundred million. Orleans is a framework that you can use to improve developer productivity as you build distributed systems. A big part about Orleans is you can also scale out your game, and so you may not know how many users that you are going to have, and that number may be different when you launch versus long term. And so Orleans also allows you to scale out over time, making sure that the services that you build today are the same ones that you're able to run tomorrow without having to re-architect everything. We use it to power a lot of internal Microsoft services, and we've made it available open source for the last few years to allow everyone to build the same services that we build without having to solve the same problems. I've used Orleans for the past 7 years, from an early project in Microsoft Research through the first production service that we ran as part of Halo 4. And then we now use it for nearly all services in Halo and a bunch of the services that power PlayFab today, and we're expanding it to use it in more places now. So before I talk about Orleans, I'm going to talk a little bit about just services in general. So if you've ever built a service, this may look familiar to you. And there's a good reason for this. This is how most services are built today. There's a stateless front end, a stateless middle tier, and then you store state in the back end. And the great thing about this architecture is it works really well. Because everything's stateless and typically there's a load balancer there, you can scale up and down, you can handle failures easily. And also take machines out of service for maintenance. But typically there's tweaks that we make to this framework. So the first thing that most people do is they add a cache in the middle tier to improve the read latency, so you can get requests, so you can handle requests a little more quickly for your users. And that works all fine and good, but then as you scale out your service, maybe your storage becomes a bottleneck, and so you have to think about how you're going to handle that. You can handle that with a partition cache, where the read calls go through your cache layer, but now we've gotten a lot more complicated than that original one. So maybe it's a little bit dramatic with the fire, but the point is that this is really hard to do. A few games launch every year and immediately fall over. You can probably think of some of them that has happened to recently. It's not because they have bad developers. It's definitely not because they didn't work hard enough. It's because this is really complicated to get right. And here's just some of the challenges that you have as you're building out the services. When you're building these layers, you have to maintain a balance of machines across the layers so one layer doesn't overload the next. There's also multiple concurrent writes happening in storage, and you can try to be smart about planning your storage schema. You can use database features to handle concurrency, but now you're dependent on your storage layer, and again, that can become a bottleneck. Caching solves a bunch of these problems, but it introduces a bunch more problems. Cache invalidation has been called one of the two hardest problems in computer science. Partitioning your cache is a particularly challenging problem, and I talked about a partition cache layer, but you may also have to partition the cache at your middle tier so that you don't overflow the memory that you have at that layer. And then finally, the cold cache. So as you spin machines up and down, as you lose machines, you may have to serve requests from that are not currently in the cache, and that, if you're not able to handle that, you actually will never be able to recover, and it can take down your entire service. After all these patches, the failure recovery is no longer simple, the scale in and out are no longer simple, and so what we wanted to do is figure out, is there a better way that we can build services? I joined 343 Industries back when we were starting to build the services for Halo 4, and it was an opportunity for us to rethink the architecture. At the time, everything was moving to the cloud. It's kind of even more true today. And so we didn't have the term at the time, but we wanted to build cloud-native services and have a framework for doing so. We wanted to take advantage of the dynamic scale that was offered in the public cloud, and we also wanted to make life easier for our developers. We wanted a natural model that matched the way that games are built, with no inherent bottlenecks or single point of failure. Basically, we wanted our developers to be able to focus on the features of our game, not the infrastructure to run them. And As we were doing this and trying to figure out what was the right way to build this framework, we started talking to other teams, and one of them was a team in Microsoft Research called the Orleans team that was working on something that sounded very similar to us. So what did we do? Well, the first thing that we did is we partitioned our state across the middle tier. And this has the advantage of you can route your requests to a single authoritative source per entity, which allows you to make decisions locally without having to coordinate across an entire cluster of machines. Storage is used only for persistence, and this means the storage layer is much dumber and can scale out much more easily, and you can even swap storage layers in and out because there's so few requirements of that. Now, that helped our scale, but it didn't really make anything simpler for our developers. Developers shouldn't really have to think about VMs and clusters. We want them to be thinking about what's natural for developers, and that's objects. In Orleans, you think about virtual objects called grains. And virtual objects are, think of them kind of the same way that you think about virtual memory. Virtual memory is kind of amazing. We don't think about it a lot of time. But when's the last time you wrote a program where you knew where a memory address was on a particular memory stick? You don't, and you don't have to because of virtual memory. In fact, when you access a piece of memory, you don't even know whether that memory is on a memory stick or maybe it's on disk and gets paged into memory just in time for your request. Similarly, objects in Orleans are pulled in just in time to handle the requests that you're making, and then are garbage collected as needed. This allows us to have billions of virtual objects because you probably only need a few million of them in memory at any given time. So I've talked a lot about and shown a bunch of pictures, but let's get to the code. What does this actually look like for developers building these services? Well, the first thing that you have to do when you're building an Orleans service is to define the grain interface. And this is about as simple as you can get. There's a single method on this interface. The only requirement here is that it has to be asynchronous, but otherwise you can define what other methods you want on this grain. In order to call the grain, you first call getGrain, and that gives you back a proxy object, and then you just call a method on that grain, about as simple as you can get. And here I have another line that prints out the result of that call. Now, one thing to note here is there's no explicit activation of the grain. This code doesn't know whether that grain existed when the method called, and it doesn't have to care. If it already existed, the message will be routed to it. If not, it will be created, and then the message will be sent there. So now an example of how you could actually write the grain implementation, kind of about as simple as you can get, but what I want to note here is that I'm incrementing the user count here, and I'm not using any interlocked operations, and I'm not doing any locking. This is safe because Orleans also guarantees that there's only one single request being processed at any given time per grain, and then allows you to scale out by having many grains throughout the system. This is a powerful thing for developers because it lets you, for example, start a match when the match is full, or reject players once the match starts. You don't have to think about concurrency, and you have a full view of the state of the grain while you're doing this. Very useful for developers. We'll get a little more complicated here, so now we're going to handle some errors. You can see I've added a few more lines. It's basically a try-catch, and it more or less works exactly like you would expect it to do. In this case, let's say that if you look at the animation, the client is calling into the match grain, and now we've made it maybe slightly more complicated, so that match grain has to do something else. It's going to call into a player grain to maybe get the avatar for that player. Well, for whatever reason, there's some fault in the player. That, without any intervention from the programmer, is propagated up the stack across machine boundaries, and you can handle it at any layer. In this case, it makes it all the way back to the client, and we're able to print out a message saying that we were unable to join that match without the developer having to manage all of the communication in between. So that's an example. Here's a real service that we built. This is actually the first service that we put into production on Orleans. It's called the Present Service, and we built it for Halo 4. So when an Xbox was playing Halo 4, it would actually regularly send heartbeats to our service. The router grain would unpack these enough so that it could route the messages to the game session grain, and then the game session grain would notify all of the players that were in that session so that they could report what was happening with each of the individual players. The observer was able, when this might be a mobile client or a web page, could call into the player grain to find the current state of every player in the system, and then if it wanted to, it could get near real-time updates by calling into the game session grain and subscribing to notifications for what was going on. This allowed us to create experiences where on your phone you could see what was going on in real time in the game. One of the amazing things about this system is that it scaled almost linearly. So here's something from a paper that's linked there. So this was the scale of the system, and you can see as we go from 25 to 125 servers, the throughput increases with the number of servers. This is kind of a simple thing that you expect to do, but it's rarely true as you build services. Most of the time, you actually see it curve, and then if you keep adding services, it will actually continue to drop as the communication between them becomes higher than the throughput advantage that you're getting. Orleans does this by default, and that's what allows it to be scalable as you build out your systems. We were so happy with the development experience as well as the scale of this that we then used Orleans for almost all of the services that are powering the games, the website, and companion apps for Halo today. Most of those services are a lot simpler than the one that I just showed up here. You don't need a complex call graph in order to benefit from Orleans, state management, and concurrency controls. So grains are great for processing entities. But what if you want to do things across certain entities? So in this case, Master Chief wants to trade weapons with Anya. Well, the kind of generally accepted practice today in distributed systems is that it will be eventually consistent. It works, but it's hard to get right. And also, it's hard to explain to players. And so you need to think about it even as you're designing your game, how you're going to make it so that players can understand that maybe the weapon actually disappears before you get the new one. So the normal case is you might take both of the weapons away, and then you're going to award them to the other player, but in the middle, maybe your machine crashes. It comes back up, you've lost your in-memory state, and now both of those weapons are gone. The players didn't get what they were expecting. You can definitely handle this, but it's really hard to get right. There's a solution for this that's been around for a long time, and it's called transactions. But the problem is that people gave up on them a long time ago in distributed systems. I personally didn't think that this was possible to do at scale with the throughput that a game like Halo requires, but the guys in Microsoft Research proved me wrong. They built an early implementation of this, and we productized it in PlayFab. And so the idea is that there's no intermediate state that's exposed to the system. If you're trading weapons between the Master Chief and Anya, either they have the original weapon that they have, or they get the new weapon. And there's no way that you can have any state in between. This is another huge productivity win for developers because they don't have to worry about programming all of those edge cases. And it's a huge win for design as well because you don't have to try to figure out how to communicate to players that they're going to get their weapon eventually. So I've talked a lot about the Orleans system. And so I want to talk now about how you can be successful building out services on this system. One thing that you need is a large number of independent contexts. And the good news is that you probably have that if you're building game services. They're your players, they're your matches, they're your sessions. Just pick one and make a grain for every one of these contexts. Another thing that's important is to think about what are the call patterns that you're going to have between your grains. So it looks like a method call, but a lot of the method calls on grains are going to end up being remote calls. So you don't want to have individual properties pass back from each of those messages. You want to think about what the call pattern is and pass back all of the properties that you're going to need for an individual request. It's also simplest if you have a directed acyclic graph of calls, but there are options that you can do. I don't have time to get into all of them, but you can look up additional features for handling more complex call patterns between grains. Today we have over 150 developers contributing to Orleans, both inside and outside of Microsoft. We have a lot of features that I don't have time to get into today, but I'm happy to talk with you at the booth if you're interested later. And we use it in many PlayStream services. We're using it today in PlayStream, multiplayer services, we use it in commerce, and we're looking at a lot more places that we can integrate it as well. So what would I recommend that you do next? Well, I would recommend that you build your next service on Orleans. If you do, you can build it faster and you can have less code to maintain. It depends on your individual service, but we've seen between 3 and 10x code reductions in the amount of code that you need in order to build a service compared to a general stateless service that you would build. If you use Orleans, it also becomes more scalable. You saw the linear scale that we were able to achieve, and we've seen that across many different services. So if you're interested, go check out the GitHub site, look at our docs and samples, and we'd love to hear your feedback. We're pretty active on the forums, on GitHub as well. There's a chat room on Gitter where we're pretty active. Drop by the booth that's right over there, or submit a pull request. It's all open source, and we'd love to see how we can continue to improve.